We previously looked at controlling inrush by slowing down the MOSFET turn on. This was in part 4 of the load switch design series. Since we still wanted the FET to turn off as fast as possible, a BJT source to gate clamp was added. As shown, the design worked, but how robust is it? Let's say you wanted to limit the on-state bias current a bit more and increased R2 to 50K. In this case, the fast current turn-off no longer works, and the FET takes much longer to turn off. What about threshold voltage variation? In part 3, this pass switch was chosen because it had less threshold variation than other options, but it still varies between 1 and 2.1 volts. The SPICE model the manufacturer provides sets the threshold to 1.85 volts towards the high end of the range. But you can actually edit the SPICE file and change the VTO, which is the V threshold value, to the minimum in the datasheet, 1 volt, to see what happens. This doesn't really make it a validated corner model, but it can still be useful as a first order stress test. Even with the stronger R2 pull-up at 24.9K, the BJT conducts briefly during turn-off, but stops conducting while the source-to-gate voltage is still high enough to support channel current in the FET. After the BJT stops conducting, the gate discharge reverts to the slow path through R2 and R limit, so the MOSFET current decays instead of snapping off. There's still voltage across the FET since the drain will take some time to reach 0 volts, and there's current flow. That means the FET is dissipating power and could exceed its safe operating area or junction temperature limit during this turn-off period. So let's see what's happening to cause this. If you redraw the circuit slightly by moving R limit, it's a bit easier to see that the source-to-gate voltage is equal to the sum of the voltage across R2 and the voltage across R limit. The voltage across R limit is also the VBE voltage of Q2, which is the clamp BJT. And we know that during turn-off, the source-to-gate voltage is going to drop from 5 to 0 volts as the FET turns off. This behavior can be modeled with a voltage divider and a diode, actually similar to the design of the enable switch in part 2. The source-to-gate voltage is obviously not a voltage source, but it can be helpful to think of it as a source that transitions from 5 to 0 volts for this exercise. It's not an exact model, it's just an abstraction that can help with intuition about the behavior of the switch at turn-off. R2 and R limit form a voltage divider, but the voltage across R limit will get clamped by Q2 VBE if it's higher than the minimum voltage to have current flow through the BJT. In reality, this minimum VBE isn't a hard threshold, it's just the VBE needed for enough conduction to mostly short out R2 and R limit. We can make the assumption that the minimum VBE is around 0.6 to 0.7 volts. The divider expression is defined first. That's straightforward, it's just a voltage divider equation. If the voltage is clamped, the current follows the BJT version of the diode equation. The clamping effect of VBE can be described either as a minimum voltage statement, or it can be described as a piecewise function that more or less says the same thing. Maybe you're already ahead of me and you see where this is going. If it works out that the divider voltage is below the minimum VBE, that means the BJT is off and it can't help speed up the turn-off of the FET, so current decays over some time instead of turning off quickly. To get a better feel for this, we can work through a couple of examples. First, let's say the source-to-gate voltage is 5 volts, so turn-off has just started. The voltage across R limit, according to the divider, would be 1.8 volts. That's much higher than what we need for the BJT to be on, so it'll definitely turn on and short out R2 and R limit. As the voltage falls, eventually it'll get to the threshold voltage that's defined in the SPICE model. That's the VTO at 1.85 volts, as mentioned earlier. In this case, the R limit voltage is 0.67 volts according to the divider. That's still good, the BJT should still be on, and that's what we saw in the sim. It worked just fine, and the current stopped quickly. What about the case where the threshold voltage does vary? If it happens to be the minimum given in the datasheet and we push it through this function, the R limit voltage is 0.36 volts. That's quite a bit lower than what you'd like to see across VBE. And as we saw earlier, we didn't get the desired effect and current took some time to drop to 0. The other case that was shown was the larger R2 to limit the on-state bias current. And again, this gives under 0.6 volts. So we can expect the BJT to stop conducting before the MOSFET enters cutoff. There's definitely other approaches to analyzing the BJT clamp, but this way seemed intuitive. Let's see how we can actually improve the design. For the first option, using the divider formula and some algebra, we can find the R limit value that will give 0.67 volts VBE at the minimum threshold voltage that could be expected. And to account for a bit of temperature variation, let's use 0.85 volts instead of 1 volt. This gives a much larger R limit than what the design had previously, 93.1K compared to 14K. We'll also need to update the C limit value since the rise time should remain the same. As long as the product of R limit and C limit is the same as before, the rise time should also remain approximately the same, and that ends up being 15 nanofarads for the C limit capacitor. The plots show the FET current at startup, and that matches up very well with the previous design. It doesn't have to be perfectly one-to-one, but you can see it's really close. The lower waveform shows turn-off, and this is interesting. With the original design, the source-to-gate voltage rapidly drops to 1.7 volts. This is below the 1.85 SPICE model setting, but not by much. The updated design drops all the way down to 0.71 volts, so there's a lot more margin for threshold voltage variation. Testing the new design against 2 threshold voltage settings in the FET model shows that the fast current turnoff is achieved in both cases. The second design option is to add a blocking diode, which will allow current flow during MOSFET turn-on and block current flow during turn-off. The analysis for this approach is similar to the original design. The C-limit capacitor current is calculated by subtracting the forward voltage of the diode from the gate voltage and dividing by R-limit. Previously, the current was just the gate voltage divided by R-limit. Basically, we're just adjusting R-limit to account for the forward voltage of the diode. At around 100 to 300 microamps, the 4148 diode forward voltage is typically on the order of 0.5 to 0.7 volts. If you check in LT SPICE using the built-in 4148 model, it's around 0.5 volts, so we'll use that. The new R-limit value accounting for this is 12K. Again, the turn-on plots look similar to the original design. For turn-off, the source-to-gate voltage drops from 1.7 volts in the original design to 0.63 with the added diode. So that definitely adds a good amount of margin for threshold voltage variation. And that's it. That's 2 ways to increase the robustness of the turn-off clamp with respect to threshold voltage variation and bias current sensitivity.